Two Friedman equations. Let me just, this one divide by 3 and this one divide by -2. Okay. So these are my Friedman equations. Now let's just get some additional equation that you can get in another way, which is just called the conservation equation. What I'm going to do is just take the derivative of the first equation. So I'm getting 2h dot equal to 8 pi g divided by 3 rho dot. So it's just the derivative of the first equation. But at the same time, we know that h dot is equal to this. So we just have to multiply it by 2h. So it will become minus 8 pi g. And there is an h rho plus p. So from that I can simplify a bit the equations and get that rho dot plus 3h rho plus p is equal to 0. So this is what is called the equation of conservation. So in the sense that if there is no expansion of the universe, remember that h says about the expansion of the universe, it's the a dot over a. If there is no expansion of the universe, the density, the derivative of it is 0, so the density is constant. So of course, if the universe is not expanding, it's the same. You have the same density. Now, if the universe increases, the density will decrease also. So you have some form of dilution in the universe. So this is what this equation is telling us. But we need to know what is the pressure as a function of density to introduce some sort of equation of state. You have different type of fluids that you can consider. And depending on this fluid, you can get actually what is the relation here. So let's, I don't know if we will do it now or yes. So there are two types of fluids usually that are considered in cosmology. One is dust. So for dust, what you have is that pressure is 0. I mean, it doesn't mean that the pressure is exactly 0. It's just that you consider some type of fluid where the pressure is really negligible compared to the density. So mostly what you have is density. If you take radiation or any relativistic type of particles, you can use statistical physics to show that in this case the pressure is 1/3 of the density. So these are different type of equation of states which are telling you for the fluid that you will consider what is the relation between pressure and density. So more generically, I can define an equation of state which is going to be which I will define like pressure is equal to a W times density. So for dust, we have W equal to 0. For radiation, we have W equal to 1/3. Okay. So this is something that we will consider for different type of fluids. You can have different equation of states, and then you can calculate everything that you need. Imagine that we consider the generic case that the pressure is W times the density, but it's not that generic because I will consider the W is a constant. The most generic thing will be that W doesn't depend on time, is not a constant. So I just replace in this equation. Thanks. I will just replace in this equation, and what I get is that rho dot plus 3h. I will factorize by the density here, and I get 1 plus P divided by the density is W. Okay, so I have this equation here. Now this equation can be solved easily. What you have is that rho dot divided by the density is equal to minus 3, 1 plus W, H, and H, remember that it is just A dot over A. So if W is constant, I can integrate that and get that the log of the density is equal to minus 3, 1 plus W, log of A, plus some constant of integration. So then what we have is that the density is that constant of integration, A, the scale factor, 3, 1 plus W. So this is the density that we have depending on the scale factor of the universe. Now let's go back to the examples. When you have dust, W is 0. So if W is 0, you have a density which goes like rho 0 divided by A3. So W is 0, you have A3. A3 actually is like the volume of the universe. So what you are saying is just that the density got diluted in the universe. The universe increases by a scale factor A. If you take a box, a cube, the volume is A3. So the density decreases because it's a density of energy. It decreases with the volume. So that is what it says for dust. But if you consider radiation, W is 1/3. So 1/3 plus 1 is 4/3 times 3, it's 4. So for radiation, you get 4 actually. So for radiation, actually, you lose much more energy. First, you lose energy by the expansion of the universe, but you lose a bit more energy because actually radiation is also redshifted. During the propagation, it loses energy because of what is called the redshift. When you have a wave like that of the photon, for example, the expansion of the universe stretches actually this wave, and you know that the energy is proportional is hc divided by lambda. So actually if lambda increases, the energy decreases. So the photons, actually the radiation, decrease its energy. So this is why you have actually a bit more, you lose a bit more energy for radiation. So you can calculate for any kind of fluid. You can take any type of fluid and you will get what you need on its evolution. So we know that density goes like the inverse of the volume or the inverse of A4 actually. Okay, so let's go back to the idea that I was talking about this morning on the acceleration. So remember that the acceleration we found that the acceleration divided by A was something like minus 4 pi g divided by 3 density plus 3p. So if I replace here, I get minus 4 pi g density divided by 3, 1 plus 3w. Okay, so acceleration means that because there is a minus sign that this is negative, so acceleration means that w has to be less than minus 1/3. So that is what means acceleration. It's exactly what we wrote this morning, that the pressure plus 3 times the density should be negative. So written it in this way. So remember that dust, W is 0, radiation, W is 1/3. So clearly with standard matter, you will never get acceleration. Okay, so this is what we are left with, that we have to find something which produces some W less than minus 1/3. The additional thing that we can do is actually solve now this equation and complete completely the problem that we started, which is to find the expansion of the universe. So this is the density we get here. We can replace it in this equation. So you get that h squared is equal to some constant, 8 pi g rho 0 divided by 3. And you get some 1 over A3, 1 plus W. Okay, and remember that H is A dot squared by A squared. Let us call all this some constant A, not to write it all the time. So what you get is that A dot is square root of A, and then you have an A squared there. So you have an a squared minus 3, it's minus 1, so you have a minus half, and then you have a minus 3 half w. Okay, this is a differential equation that you can integrate also. So you will get that a power 1 half plus 3 half w will be proportional to time. So means that the scale factor will be proportional to t 2 over 1 plus 3w. There is, it's 1 half, it goes 3 half, so it's 2 over 3, 1 plus w. Okay. Okay, so with that, we completed completely our work is to find what is the expansion of the universe, what is the density of matter, etc. So this is what Einstein's theory is telling us. So again, we assume just two things. One is the theory of Einstein, two is homogeneity and isotropy. Then the calculation is simple, and it tells us that the universe is expanding, first of all. It's expanding with a scale factor which goes like that. So if you take dust, for example, you take a universe with only dust, then the scale factor goes like 2/3. Okay, so the scale factor grows with time, and it goes like this. And of course, if you take the second derivative, this will be negative, so you have deceleration. Now, if you take radiation, this is going to be 1 half, so the scale factor goes like square root of t, etc. So you can calculate all this and things like that. So with that, we completed our job. But now, what are the problems with this? The problem is the following, is that, as I said this morning, we need an acceleration of the universe. And actually, we don't need one acceleration, but we need two accelerations. In the standard theory, in cosmology, the universe accelerated twice. So if we start from the beginning, not the Big Bang. Big Bang is something we don't know. I mean, the initial singularity is a problem that we don't know. The theory doesn't work in that regime. But we have some universe and expanding. There is a first acceleration, which is called inflation. So the universe goes very fast and then slows down and starts growing slowly. And then, since 4.5 billion years, it gets a second acceleration. And we are living in that second acceleration. Universe accelerates, and this is what we call dark energy. So we have two accelerations in the universe. Why we call it dark energy is because imagine that Big Bang is an original force, an original energy. All particles are pushed away. So it's like me throwing something. If I throw something, it goes with some acceleration, and because of friction and things like that, it slows down, and then at some point of time it stops. The velocity will stop. So here there are the two particles which are going far from each other, but they attract each other because of gravity. So they should slow down, slow down, slow down, slow down, and at some point of time they should stop, and because of gravity go back together. So that was the idea. But actually not at all. The universe is expanding, but they accelerate. So it means that there is some energy which is pushing that, and because we don't observe this energy, we call it dark energy. So this is the second acceleration. So we have not only one acceleration, but we have to explain two accelerations, and clearly it's kind of difficult to explain it in this way. So let me just say a bit about inflation and how people come out with a solution. So inflation is the following. I don't know if you have first some questions, no? Okay, so inflation is based on something, some problem. As usual in physics, some theory comes because we are trying to solve some problem. The main problem at that time was something which is called the horizon problem. The horizon problem is the following, is that we receive some light which is coming from the CMB, and so from the very early universe. And we observe this light, which is coming from very opposite direction, with exactly the same temperature. So what we can think is that necessarily, even if a photon comes from this direction and another from this direction, if they have exactly the same temperature, means that at some point of time they were in contact. So they have some interaction. There is some kind of... yeah, I don't touch it. So there is some sort of... they had some interaction. So they thermalized in some way. And they had the same temperature. And from that they started going to each one in an opposite direction. So these two photons, which are completely coming from different directions, at some point of time they should be together. The problem is that if we take the picture back, actually this video of our universe, the universe is 13.8 billion years that we will calculate during the tutorial. And we go back actually, so these two photons which are here and here, and we go back actually, we will stop here, and they will never be in contact. So then it generates a problem. If they have never been in contact, how is it possible that they have the same temperature, that they have the same properties? This is called the horizon problem in some way. So it's a simple way to say it. And so the idea which came in the very early 80s was to say that there was an acceleration. Actually, they were in contact in the very beginning. So they thermalized, they had the same temperature, and then the universe accelerated very fast. And then after that, it started expanding normally. So now they look very, very far from each other, and we think that if we go back, they have never been in contact. But yes, they have been in contact because there was an acceleration at some point of time. So that is the inflation. So originally, inflation is to solve that, and to solve some additional problems, which is called the flatness problem and the monopole problem, which are not necessarily very important for us. But what came fundamentally with inflation is that it gives an idea about how the structures in the universe are formed. In the sense to say that in the very, very early universe, we had some quantum fluctuations. So there are fluctuations everywhere, but they are quantum. And actually the universe stretched so fast that these quantum fluctuations became much larger, and they became actually classical perturbations. So we transformed in some way quantum to classical. They became much larger. And these perturbations, this is the perturbations that we observe nowadays, which are galaxies. Means that in some part of the universe, there was a bit more matter than in some others. If I have a bit more matter here, and here there is nothing, it will attract more matter and start clustering, and will start forming galaxies. In order to reach a galaxy, what we need is just an initial perturbation, just a little bit more of matter. If we have a bit more of matter here, it will grow with time. But we need a small perturbation. That small perturbation comes from quantum fluctuations in the very early universe, and that quantum fluctuation, I have to transform it into classical transformation, perturbation, and that is inflation. So in that sense, really inflation is fundamental. It's not only to explain the horizon problem, but really to give an origin to structures, to explain how the galaxies exist. So this is why really we believe that there was an acceleration of the universe. And at the same time, what happened is that we can calculate from that various things, something which is called the power spectrum. And we can compare it to the observations from the CMB, these photons that we receive. We can see the spectrum, etc., and it's completely compatible with the observations. But to reach all that, we need an acceleration of the universe. And to do that, we needed actually something which is which has some action, and actually which is not general relativity. As I said, if you take general relativity, dust and radiation, you will never produce acceleration. So we need acceleration. And the first model, which was proposed more than 30 years ago, is called the Winsky model. So we'll start with that. And this is the first model of inflation. So the Winsky model is to say the action of general relativity. Remember that we said that we had an action like R, but I will add some correction to it, some constant r squared. And matter sector. This is not anymore general relativity. So general relativity will be just killing this. It is still an action, it's well defined, etc. There is no problem. But with this theory, I will get another equation of motion. I just have to make a variation of that. I get an equation of motion, and with that I will produce an acceleration without any exotic matter. I don't need to have some exotic matter with negative pressure, etc. I just need dust, I need radiation, and I can produce an acceleration just because the gravity sector is different now. I don't have the action, the Lagrangian proposed by Einstein. But of course, we are changing everything, 100 years of history. So we have to be consistent with everything. Is this model going to be consistent or not? I will talk about it later on. But this is the main thing about this kind of theories of modified gravity, is that we could produce some effects like acceleration of the universe without much modification, just a small correction. The origin of it, because I said that I will try to motivate also on things like origin, etc. The origin is quantum origin. People in the 70s try to calculate what is the one loop correction to the Friedman equation. In some sense, we can say to general relativity. And there are these papers by Birrell, Davis, etc. that you can look for. In 77, 78, etc. And what they found is that you have actually a term which, it's like, I mean, just an expansion, that you have a series expansion like this, and when the curvature, this tells us just the curvature. When the curvature is small, so you just have GR. So that is fine. But when you go to a regime where the curvature becomes very, very, very large, then you start having these corrections. And in the very early universe, when you have this inflation, this acceleration of the universe, this correction starts to be important. But in low regime, like the physics that we do here on Earth, on the lab, in the solar system, curvature is small. We know that Newtonian physics works perfectly fine because we don't measure much curvature. You have to go to the strong gravitational regime, then you start having this effect. Otherwise, you have only this. So the Starobinsky model is a correction at high energies, okay, at high curvature. So that is the idea, and we recover Einstein in the low energy limit. And with that, you can have an acceleration. Okay, I don't know if you have some question about it. I will talk about it more in details later on and show that actually there is some trick here. We'll talk about it, I think, on Thursday, that we can transform this theory into GR plus some scalar field. And then we will introduce all these things which are called chameleon mechanism, etc., which is a scalar field which is coupled to matter. We will go into these details, but this will be more specific. Okay. So,
normalization is correction, quantum correction, but gravity means non-linear.
Yes, no, it's the idea is not to find a complete theory of gravity, quantum theory of gravity, but even if it is not normalizable, what you can do is you can work it out perturbatively, and it's still fine theory. You work it out as an effective field theory, means that you have a cutoff, and at some point of time, in some regime, you can say this is a good approximation. Now, if you have a UV complete theory, a full theory which works for all type of energy, that is no, we don't have. But in some regime, you can say that is an effective field theory, and this is a good approach to it, okay? So, and we will see that this model actually is equivalent to the addition of a scalar field. And the additional thing is that this model is consistent with all observations. So you can calculate everything for CMB, etc. It's consistent and it works perfectly fine. So since 37 years now, this model has been, people are checking and it works fine itself. So that will be one example. This is what I mean by modified gravity theory. But people, they have looked at it in a different form. For the inflation, they look to an action of this form. Later on, we will see that they are equivalent. This is exactly the same theory. You just write it differently. Okay, so now things are, okay, the microphone. Now things are a bit different. The matter is always the same. You put dust, radiation, and whatever you want. You have Einstein, and then you have a scalar field. The scalar field, you add a kinetic term for the scalar field. What I mean by that is this. This is the kinetic term, and V is the potential. I don't know if everyone is familiar with this type of notations, etc. For the people who took GIAN and cosmology classes, yes? Okay. So this is called usually a quintessence field, and these two theories are exactly equivalent. These two theories are the same. You are just looking at it in a different way, and we will see that. It's called a conformal transformation, and they are exactly the same. This is why both theories, they are consistent, because they are actually exactly the same. So this is a way to do inflation. There, you have a way which is through extra dimensions. You know that in some theories, people are motivated by considering some more dimensions. We are not living in 3 dimensions of space plus a dimension of time, so 4 dimensions of space-time, but maybe 5, 6, 7, 10 according to string theory. So there are different dimensions, and these dimensions, they can produce an effect. Now, how do we see this dimension in an action? We will see that on Friday, how to reduce. You have a theory, imagine this is called the brain models. This is what the calculation we will do on Friday, that you have actually a space. This is 4-dimensional space, and we are living on this surface here. This is us, but actually there is an extra dimension, and a dimension y or w or whatever we call it. So actually the space-time is 5-dimensional. But because we are living just on that surface, these are called GIAN models, we are living just on that surface, we don't see the extra dimension. So this is a way to think about extra dimension. So we cannot go there. In some sense, we are constrained to live only in this brain here. So we cannot exit, so we don't see the extra dimension. And here we can actually start with some theory of gravity like Einstein and reduce that to a theory in 4 dimensions. And we will see that we will get a modification of gravity of this form actually. So how to motivate these theories of gravity? There are different ways. Quantum corrections, extra dimensions, and we will go into the details of each one. Yes?
So the next action, it is also an effective theory. It should also have
This one? Yes. Yes. So then you can think that there are additional corrections like R3, R4, or things like that.
The correction depends on alpha, right?
Yes. Yes. And alpha has to be pretty small actually. Alpha,
It is the parameter.
yes. Yes. So and the alpha tells us when the acceleration happened. So if you want the acceleration to happen in a very, very, very early universe, alpha has to be very small. Otherwise, it will happen a bit later or a bit before it starts. So you adjust the alpha on the moment when you want to have this acceleration, actually. So it's related to that.
So in fact, we are doing all these things to explain the acceleration.
Well, that is one reason, yes, yes. But another reason is to say there is no, I don't look to observations. It's just that from a fundamental theory point of view, I don't have a theory of quantum gravity.
Yeah.
But that theory, if I look at it in some sort of way of perturbatively, I will certainly get Einstein, then I will start getting some corrections to Einstein, and all that theory will be my full theory, quantum gravity theory. So these corrections can be these kind of terms. And I would like to study what are the effects of these corrections, and can I observe them or not? Can I observe quantum gravity in some sense?
Acha, means if you go back in time,
Yes.
can you observe the quantum fluctuation in time?
Yes. Quantum fluctuations, we will not observe them directly. We see them
Yeah,
through
but-
galaxies, but there are different information through CMB, etc. So people, they were calling that like quantum gravity in the sky, observing quantum effects in the sky and things like that. So because we observe this CMB, these photons, so we can guess something. So one is to say, I can, without looking to acceleration of the universe, that is from an observational point of view, is to say, I would like to see if I can measure quantum gravitational effects. The other one is to say, maybe we are not living in 4 dimensions. This is something we assume from the beginning, and we know that we should not necessarily trust our eyes in physics, in science. So we see 4 dimensions, we see that then it's 4 dimensions, but maybe not. So we have to check that also. Maybe we live in 5, 6, 7, 8. So we work with these extra dimensions, we do calculations, we get a prediction, and then we see if it works or not. And that will be the conclusion Saturday, if we see something or not. I can already tell the answer, we don't see anything so far, but we can continue a bit, a couple of years more, to see if we can see something. So these are kind of motivations, is to try to understand if we can see something beyond general relativity. So this will come all the experiments that I will talk about, and there are quite interesting experiments in the lab, because up to now, gravity was tested principally in the solar system. When you look to the sun with Mercury, with all the planets, with neutron stars, with black holes, with cosmology. But you can do gravity in a lab, like you do quantum mechanics. And there are more and more actually experiments with that, and we will talk about some of them, how you can actually get some constraints on the theory of gravity and see if it is compatible or not with this kind of thing. So this will come on Thursday and Friday. So this is some of actually the motivations, extra dimensions, and the quantum corrections to gravity. I don't know if you have some questions here. Yes.
So, do we have any perturbation in the exotic matter action? Do we have any perturbation in the exotic matter action?
What do we mean by perturbation? Perturbation, we always implement it after, in the sense that first we have, in what I did here, is to say universe is homogeneous and isotropic. And that was a comment I got at the end, is that I forgot to say that implies automatically that the density is a function just of time, and that the pressure is just a function of time. That is for homogeneity and isotropy, okay? So then I have only this, and I work, this is my background. But now I can study the perturbations of that, because at the very, very, very large scales, universe is homogeneous and isotropic, and it's pretty consistent. Now when you go at smaller scales, imagine that we go at the smallest scales, here. It's definitively not isotropic. If I see in this direction, I don't see the same thing than in this direction. So it's not isotropic. So we lose that symmetry when we go at smaller scales. So when we are at very large scales, it's homogeneous and isotropic. If we go at scales a bit smaller, it becomes to be inhomogeneous and anisotropic. And if you go at very, very small scales, it's completely inhomogeneous, completely anisotropic. So when you go at scales a bit smaller, then you can use the theory of perturbations, linear perturbations, in the sense that you say it's almost homogeneous, it's almost isotropic. So then you add the perturbation. So you consider that you have your density, and you have some perturbation of the density, and you have some perturbation of the pressure. This, of course, depends on time, x, y, z, everything. Okay, and then you study the perturbations. And this is how you do to get the formation of structures. This is how you see that actually there are galaxies, because the universe is not completely homogeneous and isotropic. Clearly, if you look to the universe, you will see that there are galaxies here, 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 here. These are the perturbations. Small perturbations like that, and you study how they grow, etc. So that will be the thing. But this is just the linear theory of perturbations. If you want to go to very, very small scales, then it becomes nonlinear physics, and it becomes much more complicated. And usually we use Newtonian physics. Newtonian physics first, because this is the only thing we can do. If you want to solve, I don't have it anymore, the Einstein equation. We know how to solve Einstein equation with two bodies. This is black hole mergers, for example. And only that, it demands a lot of energy in terms of simulation, etc. Imagine that you don't have 2 bodies, but 3 bodies. That becomes complicated because even at the classical level, Newtonian theory, 3 bodies is chaotic. So here it will become extremely difficult to solve it. So no one never did that. There are some groups in Canada, etc., which are trying, but so far they are just going. But imagine that now you don't have 2 or 3 bodies, but you have billions, which are all the stars, all the galaxies, all interacting, etc. You cannot do that. You don't have computers for that, it's impossible. So because of that, what we do is just Newtonian physics. You use Newtonian physics. Why? Because Newton works well. Every day we do experiments here, I throw that, and it follows Newtonian physics. I don't need general relativity. General relativity, I need it principally if I'm very close to a black hole in some very strong regime. Otherwise, Newtonian physics works. So in most of the cases, actually Newton physics works. So people are doing what is called n-body simulations, and they add actually some small corrections, which are called post-Newtonian parameters, etc., which are some small relativistic corrections to that, adding a bit of this in order to make it a bit more consistent. But otherwise it's Newtonian physics, because otherwise at smaller scales it becomes very difficult. I wanted to talk a bit about it, but I'm not sure I will have time, because finally I will talk about black holes and binary system and quasi-normal modes on Friday, so I don't think I will have time to talk about n-body simulations. I don't know if there are some, I think I saw some hand. There are some other questions? No? Okay. So that will be the first problem in cosmology, which is called inflation, that we know that there is an acceleration, it solves many problems, and at the same time it explains why there are structures in the universe. But to get inflation, we need to consider some actions like that. This is not GR, this is GR plus something. So this plus something, we want to know what it is. So that is the main idea. What is this plus something? So this is the first acceleration. And the second acceleration, actually, it's called dark energy. This we will study that during the tutorial, actually. During tutorial, we will see why do we need, this is a direct observation. There are some stars which are called supernova, which are, when they explode, they emit a lot of energy, and we can observe this energy, this flux, actually. We can get it on a camera, CCD camera. And we can get this flux, etc. And from that, we can actually measure, in some sense, the distance. I will explain in details during the tutorial of tomorrow. And with that, actually, because that comes back to some very fundamental question, how do we measure distances in cosmology? If I want to measure distance between here and here, I take some meter and I measure. It's easy. How do I measure the distance to the moon? How do I measure the distance to the sun? How do I measure the distance to a star? This is very difficult. I cannot just go and measure. So we have to use something else. So there are different techniques which are used. I will talk about one of them. And if I know the distance and I know the luminosity, for example, if you take something which is emitting some light, if I put it here or I put it at 10 meters, you will see that, of course, the light will be reduced just because of the distance. So if I know that, I can actually get some sort of distance, that I know what should be the light of it, but I measure some apparent luminosity, so I can guess what is the distance. And with that, actually, we can see, I will show that during the tutorial, how to explain, how to observe that there is an acceleration of the universe. And we will do this 1 sigma, 2 sigma. I will talk a bit about the statistics. That will be tomorrow to explain why do we know that there is an acceleration of the universe. But so people did the same things to say, okay, we have a second acceleration. We'll see why tomorrow with the supernova. So they say, why should not do the same thing? Let's take the same action. This action here, for example. This works. It gives an acceleration. It's called inflation. Why should we not use it twice? It will produce the other acceleration that we call dark energy. And that is perfectly fine. And they are called quintessence models. So let me go into a bit of the algebra and to see about how it produces a W less than -1/3, which means that it produces acceleration. So with that, we will see that we get an acceleration that we can call inflation or dark energy. Usually, it cannot produce both accelerations at the same time, but at least it can produce one acceleration. So you have this action there, and I'm just going to make that the variation of it is 0, like this morning, to get the Einstein equation. But I have two fields now. One is the metric, and one is the scalar field. So my action depends on the metric, and it depends on the field. So I'm going to do the variation with respect to the scalar field. To the metric will be simple also. So if I do the variation of it, so I'm getting something like that. The curvature scalar here does not depend on the scalar field, so its variation is 0. The other one is squared, so it gives minus d mu delta phi, d mu phi minus v prime of phi delta phi. Okay, so here I can do some integration by parts, so it will be plus delta phi d mu of phi, which I will write as Vox phi. So what we get is that the integral of this minus square root of g Vox phi minus v prime of phi delta phi equal to 0. So one of my equations is the following, which is called the Klein-Gordon equation. And I will have a second equation, which is if I do the variation with respect to the metric. I don't know if you have questions on the variation of this action. And the second variation actually will be variation with respect to the metric. So in this case, first I have to make a variation of this. So this will bring a minus 1/2 g mu and the action, which was r minus 1/2 d phi squared minus v phi delta g mu plus r mu delta g mu minus d mu phi d nu phi delta g mu plus the variation of the matter sector. So with that, I'm getting and plus so let me put back 16 pi g plus actually all the scalar field, which is going to be g mu phi d nu phi and the minus 1/2 okay, something like that. Let me check the sign. Maybe you get a factor 2. So here 8 pi g, yeah, you get a factor 2. Here you get a factor -4. And you get a factor 1/2. Okay, so you just check actually the algebra here. It's not complicated. So you get an action of this form. So you see that you don't have any more general relativity. You have the presence of a scalar field that produces actually also curvature. So this part I can call it some T mu of the scalar field. So I can say that this scalar field, which was in the action, is like matter also. It's like dust, it's like radiation, etc. It produces also some effects. And so I can write a T mu associated to it. So let me write it correctly. Okay. Questions so far? So maybe I will just continue there. Remember that we talked this morning about that T mu for a perfect fluid can be written in this way. So we had that T00 is the density, T11 is minus a squared times p. Okay, so let's do the same trick here, and I will calculate from this the T00. If I calculate the T00, I'm getting here a phi dot squared, and here I will get a plus, a minus 1/2 phi dot squared. So 1/2 phi dot squared and minus or plus the potential. And this I will get minus a squared 1/2 phi dot squared minus v phi. So what does it mean? It means that I'm getting some density, and then I will explain what does it mean. Let me just finish the calculation. Okay. So what we did is the following, is that you have GR, you have a scalar field, you add a scalar field. Now that scalar field actually changes things, and it looks like some fluid in the theory. It is really like a fluid. So we have now matter, we have radiation, and we have something else, which is a scalar field. That scalar field will be like, actually, like a perfect fluid. So it has a density, it has a pressure. And I can relate the density and the pressure to the characteristic of the field. So the density, which will be 1/2 of phi dot squared plus the potential that we had in the action. And the pressure will be 1/2 phi dot squared minus the potential. So we see that if the potential is large enough, the pressure can become negative and things like that. So with this, if you calculate the W, remember that W, this morning we defined it as P divided by the density. So you get 1/2 phi dot squared minus V phi divided by 1/2 phi dot squared plus V phi. So of course this can be actually less than minus 1/3 because you want an acceleration, and it's not complicated to do. If you have just that the kinetic term is negligible, you have minus v divided by plus v, you have minus 1. Minus 1 is less than minus 1/3, so you get acceleration of the universe, and you are happy with that. So people look to this kind of models, and they are called dark energy models. So I'm not going to talk about that in these lectures, actually. I'm just trying to explain what also exists. So this is one type of things to say that there is an additional scalar field. This scalar field, I can motivate it from different ways, and it is called quintessence field usually, and it exists everywhere in the universe, and it's like a fluid. And so it has some density, it has some pressure, and the density and pressure are like that, except that it has a pressure which clearly can be negative, so it's a bit exotic. A scalar field is an exotic type of matter, so it can have a negative pressure and can produce acceleration without any problems. So that is the idea of these kind of things, and with that I can produce an acceleration. But remember what we said, that producing acceleration is the easiest thing in our job. The most complicated is to be consistent with everything else, and then we will see when troubles we will start. So let me give just one reference for people interested by that. You know, then archive. So if you want to have a list of all models that people have studied, etc., there is a nice paper on archive, which is 11 11062476. So they have a list of all models of dark energy, etc., and all what people did about it, actually constraining the model. And quintessence is one of them. So it's 11062476. Questions? Yes. Who goes first?
Okay, yeah, just here the P by rho in that the dominant term is phi dot square, no? Means phi dot is appearing. Phi dot square.
No, it's not necessarily dominant. It depends actually a lot on the potential.
Yeah, that's right. Yeah, that's right. It may cancel.
Yes.
Yeah, that's right. So, does it give any spatial significance or some physical significance, phi dot square? Because phi, it represents scalar field, no? So, how we can interpret it a little bit more physically, that phi dot means it's fluctuations in scalar field.
Yeah, no, not fluctuation, just it's evolution.
Yeah.
It's we can interpret it as a kinetical energy,
Yeah.
but and the V will be the potential energy.
Yeah.
Okay, so but it's just the evolution of the scalar field. It depends on time, so it's variation actually in time. That it changes with time, so that is there is not much interpretation physical, except that it is the kinetic term of that scalar field. Yeah. So I wanted to say something about that. Yes. So the potential, if you take a potential of this form, so imagine that you have a potential which is pretty flat here, and we have the scalar field which is evolving in this potential. At the beginning, because here it's very flat, it goes very slowly. So if I interpret it as the kinetic energy, actually it will be very, very small, because the scalar field goes very slowly in some sense. So it changes very little. So at the beginning, actually the scalar field goes very slowly, so this kinetic energy will be very small compared to the value of the potential, which is this value here. This is the value of the potential. So then we get -1 and we get acceleration. But then after some point, the scalar field arrives here, and then it goes much faster. Changes, it goes pretty fast. The kinetic energy starts dominating, and we get something positive, so we don't have acceleration. So with a potential like that, you can explain that at the beginning we have an acceleration, but then the scalar field evolves, and then it falls into that, and the kinetic energy changes completely, start to dominate, and then we don't have acceleration anymore. And this is exactly what we want for inflation, for example, is that you have a universe which is accelerating, and at some point it stops. That is the main thing, not to have a permanent acceleration, is to exit from acceleration. And that gives a nice thing to exit, actually. Just during evolution, if you have a potential like that, if you can motivate from particle physics that it exists some field, scalar field, the only scalar field that we know in nature is the Higgs boson. So does the Higgs boson, or maybe another scalar field, can produce something like that, etc. So that is the thing. But mostly you motivate it from some extra dimensions, actually. I will explain how to link a scalar field to extra dimensions. This is one way to do it, actually. There was another question.
Scalar field can produce acceleration in early time also and late time also.
Yes.
But in early time, it accelerates for fraction of times, and in late time, it produces for a large amount.
Yes, that depends on the type of potential you want to put. Depending on the potential, you will have or not a permanent acceleration or not. So if you take a potential like that, as you can see, at some point of time, you might escape from the acceleration of the universe. So then you have deceleration. But if you take another type of potential, you might have always acceleration. So that depends a lot on the potential, which means on the theory that you consider. So all this is then the motivation. For dark energy, people very often take a potential, there is something which is called the Radha-Peebles potential, which is some mass divided by phi, for example. So it is a potential which goes like this. Okay, so with this potential, it's okay, you can have acceleration all the time. So really depending on the form of the potential, you will produce acceleration always, or acceleration just during some time. It depends also on initial conditions. It doesn't mean that you will have always acceleration. Depends on many things. But we will do this analysis. It's called a dynamical system analysis. And we'll see that you can have different sectors in your theory. Depending on your initial conditions, you get acceleration or not, etc.
Do we have any suitable candidate to fit in that scalar field?
The problem is that we have too many. So then it becomes not predictable much, in the sense that the same thing that to produce an acceleration is easy, to produce a scalar field is easy. It's pretty simple. I will talk about some motivations, but let me just give you one, is that I was talking about extra dimensions, but we don't observe these extra dimensions. So what people are saying is that some of the extra dimensions are compactified. What does it mean? It means this. This object, how many dimensions it has, if I'm going very, very far, you will see only this dimension and you will say it has one dimension. But if we look at it closer, I see that it has a second dimension like this. Otherwise, I will see just a line if I'm very far. So the dimensions, our space, can be like that they have some dimensions which are compactified like this, like a circle, and they are very, very small radius. So in our energies, in particle physics experiments and stuff, we don't see that. If we go at very, very high energies, means that we make a zoom, we will see actually these extra dimensions. They exist, they are compactified, but they are very, very small. So they have a radius. So this extra dimension, if you take just one extra dimension, it has a radius like this, okay? So this radius, imagine that the radius actually changes in time. It can fluctuate. So now, this radius, I will call it r, but of t. If I want, I will call it phi of t. So actually that, which is going to be called the dilaton, for example, or there are the moduli fields, this is just the radius of this extra dimension which is fluctuating. This is just the radius of that. And that is the scalar field that I can produce. I will show in the brain models another scalar field which is called the brain bending mode, which is another scalar field. So to produce scalar field is maybe one of the most easy thing. I talked about Winsky model. We'll see that it's equivalent to other scalar field. So there are also supergravity. It's another type of theories, and you generate many actually new degrees of freedom. Actually, theories, they produce a lot of fields. We don't observe them necessarily. So that's mostly the problem. Other questions?
Sir, in the dispersion region, we essentially in the high energy region. So actually, the energy we impart to the scalar field, it should be divided kinetic plus potential. I cannot give solely to the potential energy. So this assumption that V is less pi, sorry, greater than pi. So how to come over this conclusion that I should have V much greater than pi dot square, kinetic energy square.
B?
V, potential energy.
Yes. Sorry, can you repeat it again?
So actually, how we can come to this conclusion? My potential energy is much greater than this kinetic energy.
I can construct it by hand.
No, because in the high energy we cannot give all the energy to the potential energy, because there will be some problem for oscillation or something like that.
No, I mean, if the thing is that imagine that your scalar field is almost constant. If the scalar field, it's almost constant. So the scalar field depends with time. Imagine it changes very little. That is almost a constant. Okay? So the kinetic term here is 0 almost. It doesn't change much. So you have just minus a constant divided by a constant. It's -1. You have acceleration. So there is no fundamental problem. You just need that the scalar field does not evolve fast. If it evolves fast, it changes very fast. Then you don't have acceleration. But if it evolves very, very, very slowly, that it depends on time but very little, then the kinetic term here is negligible and you have acceleration.
Here is the same case, no? Here
I think his question is basically what is the initial condition that you set so that you can keep the scalar field initial energy to be very, very important. How to keep the initial condition?
Yeah, no,
Some kind of close.
yeah, no, the thing is that there are two things, as I said. First, you have the form of the potential. You have to choose correctly your potential. So you need the potential which is flat for the kinetic energy not to change much. Now, this part here flat, if you make it depend where your scalar field will start, of course. If you start here or you start here, you will have much longer or shorter, etc. The initial conditions, there is no theory for that. What you say is that I start the universe with these initial conditions, and then it works. Now, if you want a theory which explains initial conditions, you will not get it. In physics, most of the time, you work that as an effective field theory, in the sense that you write something which is consistent, it works well, it gives predictions, and that's enough for us. You cannot have a theory of everything, explaining everything, all initial conditions are. Why the gravitation constant has its value? Why the Planck constant has exactly its value, etc. It's something which you don't have answers to that. So let me just maybe finish about that just briefly on what is called the cosmological constant problem. The cosmological constant problem is to adjust the constant in the theory. And so imagine that you have a scalar field, but just that the scalar field does not evolve. So it's a constant. Okay? So you have just this divided by this, so it's -1. So for a cosmological constant, W is -1. And -1 produces acceleration. Now, how do you get a constant in your theory? It's what is called vacuum energy. Vacuum energy is something which is observed. You all know the Casimir effect in quantum mechanics, that you take two plates like that, and vacuum doesn't exist, as we know in classical physics. In classical physics, you say that if I remove all particles, this is vacuum. No. Because of the Heisenberg principle, you know that you cannot have completely no energy in a vacuum. Instead, there will be always fluctuations. So the vacuum produces some energy during a time which is very short, and that energy disappears, etc. But actually, it has some effects. And this Casimir effect, which is well studied, well observed in a lab, etc., proves that it exists. So we know that vacuum energy exists. There is the lamp shift effect also, etc. So now what you get this, and you do the calculations from particle physics, and you calculate how much vacuum energy or density of it you have in the universe, and you get some prediction. You compare it to the observation, it doesn't work very well, but that's not really a problem. You just add some constant which absorbs the big thing inside, it's called a normalization, and that's it. The big problem is when you go to quantum corrections, you calculate what is known as one loop correction, two loop corrections, etc. And every time you calculate that, the fine tuning that you had before, you are just killing it. So the cosmological constant problem, there are some reviews of that if you are interested, or we can talk about it later on. It's related to something which is called the fine-tuning problem, is that you have to adjust the things at each order. Every time you go to some loop correction, you have to adjust all parameters, but you have to adjust them so much that it becomes just ridiculous. That, for example, at first order, you have to fix a parameter. Let's write it like this. The parameter lambda, which is a constant, you have to write it something like this. I will just, I think there are 47 zeros. So you have 47 zeros and you have a 1 here, sorry. And you have a 1 here. So you need a constant which has this value actually. You have 47 here, zeros that you have to consider. If you change 1 0, then you don't have the universe we have. It's not compatible. So all these zeros are all very, very important. This is really an extreme fine-tuning. It's extremely deep, actually, fine-tuning. You have to start with the exact value, but actually it's not exactly completely the problem. But now you have this vacuum energy, you calculate corrections to that because there are always fluctuations. These fluctuations will add something because you can adjust lambda to be that. Imagine that we are completely crazy and we say, yeah, the universe started with this value. Fine. But then you calculate corrections and it changes completely the parameters here. So at each order, you calculate something which actually spoils completely the fine-tuning you did before. It's not at all stable. That what we want is stability, that you fine-tune some parameter and then it stays like that. It's stable, that parameter. But here it's not the case. It's completely unstable parameter. Every time you go to some loop correction, every time you get some new number, etc., and it doesn't work. That is the fundamental problem of the cosmological constant problem. So we can explain acceleration with a constant, but it comes with a cost which is important. But we have to say that this is a simple model and consistent with all observations. There is not a single observation which says it's not lambda. Everything says that it's lambda. So it seems that it is that, but we have a fundamental problem, which is how to explain its value, how to explain this. So I was saying that also in South Africa, so let me just say it again here, in something which is that comes from string theory. Just to finish with that, with something which is not completely scientific argument, which is to say, we don't have only one universe, but we have not an infinite, but 10 to 500 type different universes. You have different parallel universes. We are in one of them, and there are plenty of other universes. In each universe, you have a lambda with a different value. So all possible values exist. So if we are in this lambda is just one of these universes, but everything else exists. So the other universes, they have a different lambda, but they produce the universe which is not viable. You don't have galaxies there, etc., because lambda is too large or too small, etc. So we are in the universe where lambda is this. So why not? Because sometimes we try to understand fine-tuning from fundamental principles and it doesn't work very well. So let me give you a problem, which is the following. If you look to the sky, you look to the size of the moon and the size of the sun. These two objects in the sky, they have exactly the same size. And because of that, we have eclipses, etc. And that is fantastic because it influenced so much the history of mankind, actually. All civilizations study the eclipses and try to predict eclipses. It's a fantastic thing. But why do they have exactly the same size? If the moon was a bit closer or a bit more far, because we know that they don't have the same size, the sun is much bigger. It's just that it is exactly at the right position to give exactly the same size. Why that? It's just a coincidence. So we could say that there is a huge fine-tuning there, that it is exactly at the position in such a way that the two have the same size. If you try to understand that from fundamental physics, you will never understand it. If you try to explain that by Newtonian theory, you will never explain it. It's just a coincidence. So why this coincidence happens, maybe you can say that there is not only our galaxy, there are billions of galaxies and all situations exist. There are some planets which do have two stars, some have one star, one moon, etc. and all type of positions exist. And we are living in the one where both are the same apparent size. But everything exists. So if you increase the statistics, you say that everything exists, then the probability that we are in one of them is 1. So here it's the same. It's to say, if finally we have a problem with this fine-tuning, by increasing the number of universes, then you are happy. You can say, yeah, everything exists, so we're happy with that. The only problem is that the first one, we can check it. We can go to other galaxies and see that there are all kinds of situations which exist. This we cannot try it. we cannot go to other universes. So this is why that makes it not really a physical theory. So that is in some way actually the dark energy.
Yeah, I'm just asking. So you are saying that this Earth, Sun, Moon system, they are more stable orbits for Moon?
No.
More than
No, this is what I'm saying, is that we cannot explain it from a fundamental theory. It's just a coincidence.
But isn't that okay? So that says that there can be more stable orbits, right? Because the Moon is going around Sun, around Earth, with the Sun there. So the orbit is a stable orbit, fine. You can calculate it, fine. So if you can have other distances where Moon can also have a stable orbit, that means in this system you can have more than one stable orbit. This I am a little bit confused.
In which?
That you are saying that this distance can be anything. It's just a coincidence that this distance is there. That means there can be more other orbits is possible. Actually.
Yes. Yes.
So
I mean,
this mass system is taking this mass of Sun, Earth, and Moon, the gravitational field, and everything.
yes.
This mass system can have other stable orbits.
Yes, it depends on the angular momentum.
Yeah, that's what I'm saying.
Yes. So
But
depending.
angular momentum comes when things, when the star sort of explode and you get all these things. So that the angular momentum conservation gives those things.
Yes. Yes, but you see that it depends a lot on the number of objects that you have. So, for example, one is to change this orbit just by changing masses, of course, but you can change also by the number of objects that you have.
Okay, you are saying the number of objects may be a coincidence. That you are saying?
Yeah. Or the number of objects is also changing these orbits, of course. So if you are trying to tell that the Moon is exactly at the right position because of stability of orbits, this I will not.
Isn't that this number of orbits?
Yeah, but then you are just pushing the problem in another one. Why do you have this angular momentum?
No, I mean, what I'm saying that given that this number of planets are there, then it is a unique system.
Yes. But then we are just pushing back the, yes. Yeah. So, okay, so that is the other problem, which is the dark energy problem. So I just finished with that actually on this basic things of cosmology. I will go more to gravity and perturbations and tests of GR. So tomorrow I'm going to do the test of GR. And yes, exactly.
5 minutes, 10 minute break.
Yeah.
And then we come to demo for.
Okay.
All right.
Okay. Yeah.
Thanks.
Thank you.